Hello and welcome to another pre-calculus lesson. Today's lesson we'll talk about binomials. Now we know a binomial is an expression that consists of two terms and it is generally of the form a plus b, where a and b can be numbers, it can be variables, or they're both. Examples include things like x plus y and 3x minus 7. Notice there are two terms to either side of a plus or minus sign. Another example that you might want to think of is something like 4x plus 8, where 4x is the first term and 8 is the second term. It is a binomial because it has two terms separated here by a plus sign. So the signs must be either plus or minus, and then two terms for it to be a binomial. Now we consider binomial expansion. Let's look at two terms, a plus b all raised to the power 0. A plus b all raised to the power 0 is equal to 1 because any non-zero number raised to the power 0 is equal to 1. Then a plus b raised to the 1 is just a plus b itself. So that's going to be a plus b. We put some coefficients in front of the a and the b here just for showing the coefficients, but it's just a plus b. But if we want to think of the coefficients, then a is just the same as 1a, and b is just the same as 1b. Now let's look at a plus b squared. A plus b squared is the same as a plus b times a plus b, which when you expand that a little bit more, bringing like terms together, you will have a squared plus 2ab plus b squared. And if we like to think of the coefficients again in front of these variables, it'll be 1 in front of the a squared. Here's a 2 in front of the ab already, and a 1 in front of the b squared. Then a plus b to the third power is going to be a cubed plus 3a squared b plus 3ab squared plus b cubed again. Think about the coefficients. Is a 1 here in front of the a cubed when we think of the coefficients. If we're not think necessarily writing as to write the coefficients, then you would just write it as a cubed. But today we are focusing a bit on the coefficients that's in front of them. So it's just for the lesson that we're going to write 1a cubed. All right, then there's a 3 here in front of the a squared b and another 3 here in front of the ab squared. And then finally, even though there was no coefficient to begin with in front of the b cube, we know it's a 1 because there's a b cube here. So we can continue working these out. We have worked out the above, but we can continue working these out to another level, to the 4th power and to the 5th and so on. What you will notice when you're doing this is that there's a pattern. So instead of doing the all the expansions out to find the coefficients, you could just look for a pattern here. So here I've labeled them level 0, level 1, level 2, level 3, level 4, and so on, just to line them up with your exponents. In some books, they will call the first one level 1. It is not a big deal. I've just noted it here to match the 0 with the 0, the 1 with the 1, and so on and so forth. All right, so as long as you remember you're starting at 0, then when we say 3, we know it's to the 3rd power. All right? But even though it's level 3, it is in the 4th line. So if you want to think of, the lines 1, 2, 3, 4, then if you want to, you can think of it that way. All right, if you notice, then there's a pattern here. There's a 1 at the top, then there's a 1 and a 1, then there's a 1, 2, 1. That's a pattern in terms of the coefficient, and a 1, 3, 3, 1. Now they have given this pattern named after some person, a guy by the name of Pascal, and so they have called it Pascal's triangle, which we will get to in a bit. But then we're going to look at a way for arriving at this pattern. So we had coefficients when it was to the 0th power, there was a coefficient of 1. When it was to the first power, it was a 1 and then a 1. Then when it was to the second power, it was a 1, 2, and a 1. And to the third power, it was a 1, 3, 3, and 1. And then to the fourth power, we would not have worked this out as yet, but when you get some time for yourself, you can go ahead and expand it out to the fourth, the fifth, and the sixth power, and you will find that you will have these coefficients in the front: 1, 4, 6, 4, 1, and then 1, 5, 10, 10, 5, 1, and then 1, 6, 15, 20, 15, 6, 1. And also, you notice there that is a pattern in the way that, this looks like a triangle, by the way. And so that's why it was called a triangle, and then they named it after somebody. You notice here that if you add numbers from the top, you get to the next level. For example, the 1 and the 1, right? Notice they are all ones on the outside, but if you think about the inside number and there's a 2 here, you could think of adding a 1 plus the 1 above it to get 2. So you're adding the numbers above them, right, to get the central number. All right, so for the 3 here, you add a 1 plus 2 here, and for the next 3 here, add 2 plus 1. All right, for the 4 here, you add 1 plus 3. For the 6 here, you add 3 plus 3. For this 4, you add 3 plus 1, and so on. For this 5, you'll be adding 1 plus 4. For this 6, you're adding 4 plus 6. For this 10, you'll be adding 4 plus 6. For this 10, you're adding 6 plus 4. And for this 5, you'll be adding 4 plus 1. And continuing that way, for this 1, you just write a 1. But here, you're adding 1 plus 5 to get 6. 5 plus 10 to get 15, 10 plus 10 to get 20, 10 plus 5 to get 15, 5 plus 1 to get 6, and so on. So you notice there's a pattern, right? And this pattern here that you see, right, was later named Pascal's triangle, right? Because Pascal's triangle, therefore, is looking at the coefficients of the expansions. You will see that pattern going 1, 1, right here, and 1, 2, 1 right here, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. So it's named Pascal's triangle. And this is a way that we can use to quickly get the coefficients, right? And if we know that there are these coefficients already here because of the way that the pattern is, then there might be a quicker way to get to what the solution of the expansion would be, instead of, when you get to higher levels, you got to multiply all of these variables and then finding like terms and so on. You could just find a quicker way using Pascal's triangle. So that is what it is. So by definition, Pascal's triangle is a triangle array of numbers where each number is the sum of the two numbers directly above it. And the top and the sides of the triangle are always ones. So if you look at the top and look at the sides, you notice they are always ones. And then the others in the middle are the sums of the numbers directly above that number, okay? So how can we use Pascal's triangle? How can we use it now to get to, the binomial expansion that we just did in a little bit quicker way than we would have if we just multiplied them out and expanded them piece by piece. And here's how you do it. We follow these steps. The first step is to determine which row of Pascal's triangle corresponds to the power. So if you're, in the first row, that would be to the power 0 and so on, right? Or if you look at what I did with, the first row is level 0, so that corresponds to the exponent 0, and then, coming down, finding out what the expansion is, right? So then if you're thinking about the row itself, we're going to say, okay, row corresponds to the number that's 1 below it. So if you think about, when I had level 0, you thought of that as row 1. If you think in terms of row, then you're going to do n minus 1, which would be the 0th power. If you look at row 1, so row 1 corresponds to, row 1 is level 0, so that would correspond to the exponent 0, and so on. Then step 2 is the terms in the rows represent a binomial coefficients, right? So the terms of the row represent the binomial coefficient. So if you have 1, 2, 1, that will be the binomial coefficient, on the power 2, right? And 1, 3, 3, 1 would be the binomial coefficients on the power 3, and so on, right? So each of these coefficients is multiplied with decreasing powers of the exponents a and increasing powers of the exponent b. So for example, when we did a plus b, if you look at a plus b to the 4th power, all right, you would look at level 4, or the 5th row of Pascal's triangle, and that would be the row 1, 4, 6, 4, 1. Right? And so what would happen, you would put these 1, 4, 6, 4, 1 in the order. Right after the plus sign, you put 1 first, and then 4, and then 6, and then 4, and then 1. And then what do you do afterwards with the powers? Then you would write a with the highest power and then decreasing. So a would be to the 4th power here. So you start with a to the 4th, then a to the 3rd, then a to the 2nd, then a to the 1st, which is just a, and then a to the 0 power, which is 1, so you don't put an a there, right? So notice the last part, there's no a. Then when you go with b now, you're going with increasing powers of b. So you're going to start with b to the 0, but b to the 0 is 1, so you don't put a b right here. There's no b right here, but then it's going to be b to the 1, then b to the 2, then b to the 3, then b to the 4. So the first binomial term, the first term, goes with decreasing powers, beginning with the highest power. The second one goes with increasing powers from 0 up to the highest power, which is 4, right? In this case. Okay, so that is how you use Pascal's triangle, right? So here's an example here. Pretty much the same example, but written in a different way. If we're going to expand a plus b to the 4th power using Pascal's triangle. So the coefficients here are 1, 4, 6, 4, and 1. And then here I write the b to the 0, right? So you start with a again. No, first of all, you write the coefficients 1, 4, 6, 4, and 1. And then write a to the 4th power, then to the 3rd, then to the 2nd, then to the 1st, and then to the 0th power. And then start with b from the 0th power to the 1st, to the 2nd power, then b to the 3rd, then b to the 4th, right? So notice then for a, the exponents are decreasing beginning with 4, and for b, the exponents are increasing beginning with 0. All right, and if we simplify this expression up here, we have a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th power. So that is how you use Pascal's triangle. All right, and that is where we end this video. Thank you for watching. Next one, we will continue talking about the binomial theorem, but this one is on the use of the Pascal's triangle for binomial expansion. Thank you very much.